Let's discuss in this class the motional EMF, electromagnetic force that is developed across the two ends of a rod, conducting rod, when it is moved in a magnetic field. Let's consider a conducting rod of length L and let us take V as its velocity. It is moving downward and the magnetic field is directed inward. Then it is seen that between the two ends AB a potential difference is developed. Now we can't explain it here that this EMF is because of flux change. We have just a conducting rod, so no flux is changing as such. But when it is moving downward, even then there is a potential difference developed between A and B. And this happens because of the Lorentz force. A force acts on the electrons because they are moving in a magnetic field, the direction of which can be found from using this expression. We can find out the direction of this force on the electron, or we can find out it by using Fleming's left hand rule if it is moving perpendicularly. So there are electrons in this rod. Electrons are moving downward because the rod is moving downward, so all electrons also have a downward velocity. I can apply Fleming's left hand rule here because the motion is perpendicular to the magnetic field. Forefinger needs to be in the direction of the magnetic field and this central finger in the direction of current. So if electrons are moving downward because of the movement of the rod, it means this is to be kept upward. This is the direction of force on electron. It means this end becomes negative and this end becomes positive. Electrons are coming in this direction. Due to this motion of electron towards A, so when the rod is moving downward, the electrons are getting collected at this end A because of the force on these charged particles due to magnetic field. An electric field is set up. What is the direction of the electric field always? We find out the direction of force on positive charge, and whatever is the direction of force on the positive charge, that is the direction of the electric field. Electric field is this. And electrons experience force opposite to the electric field. So it means electrons experience force QVB in this direction, and when due to this movement this electric field starts developing between the two ends, then this electric field will stop the motion of electrons. Initially, distribution of electrons random. When it moves down, electrons start getting collected at this point, which generates an electric field between the two. And this direction of the electric field is such that now the electrons experience force in this direction. So when these two forces are balanced, the movement of electrons towards A will stop. So QVB, when this force on electron is equal to EE, if E is the electric field developed here and E is the charge on electron. Here also I can write it E, charge on electron. So V is E. We can write electric field in terms of potential also. V upon L to V is VBL. So this is the potential difference developed between A and B, with B as positive and A as negative. In whatever direction it is moving, upward, downward, right, left, you can apply this rule to find out in which direction electrons will collect. So this is the induced EMF between the two ends AB. The cause of which is the force on the moving electrons in the magnetic field. No flux change. Okay. I have taken here a specific case in which the rod is moving perpendicular to the magnetic field. If it is not perpendicular, we have to take that component of magnetic field which is perpendicular to this rod actually. So if the rod makes an angle of theta with the field direction, then one component of magnetic field, B cos theta, will be along the field. This will not cause any potential difference. It is B sin theta, perpendicular component, which is responsible. So in that case, we can generalize the expression as BBL sin theta. Now I will take some examples where we use this concept of motional EMF. It's a very common example that we have. We have a wheel and I have made 4 spokes in it. And many times we are asked to calculate the potential difference between the point O and A. That is the point on the rim and the axle. Now how do we calculate when we have this is conducting. So it's a conducting rod actually moving in a magnetic field. So in this case also, let us see what happens and why there is why there is EMF. This is the rod. This end is fixed now. In the earlier case, I have taken that the rod is moving in a magnetic field uniformly. Each part of the rod is moving with the velocity v, but here it is not so. I have fixed one end of the rod and the other one is moving anti-clockwise or clockwise, whatever. There is again an induced EMF between O and A. We can again use Fleming's left hand rule to find out the direction of force on the electron and the EMF that is developed between O and A. Let this length be L. And now let me take the motion of this rod as anti-clockwise. What is the direction of force? If the electron is moving like this, forefinger in the direction of the field, central finger opposite to the direction of electron, because this needs to be. So if the electron is moving up, so the force is towards A. Now when this electron is actually moving on a circular path, and at every point the direction of force, it will be radial towards this end A. So when it is moving downward, A, this end will become negative and this end will be positive. So axle will be positive and the point at the other end, this will be negative. See the direction of force. Force up, this in the direction of positive, this is the direction of force on electron. So this end will become negative. And how will we calculate how much is the EMF? This is negative, this is positive, and it is moving. Let me take the angular velocity as omega. And we have just done VBL. This is the induced EMF for a length L. Now every part of this rod has different V. Omega is same. So let us take a very small part of this rod, say of length dx at a distance x. So we can find out the EMF for this dx. How much that will be? V, B, length. What is the V of this part? R omega. So X omega B dx. This will be the EMF for this length, elementary length ds. Total EMF will be integration of this from 0 to L. Omega B x dx. X dx becomes x square by 2. Unit 0 to L, so L square by 2. Induced EMF is omega B L square by 2. This is the induced EMF between the two ends of the rod. And again, it is because of the force on electrons moving in a magnetic field. Now, if coming back to this same problem, if I gave you that there are 10 spokes or 20 spokes, what is the net EMF between axle and the rim? So, will it be, say, for 10 spokes, will it be 10 times of this or will it be same? So, the answer is whether we are using 10 spokes, 20 spokes or whatever is the number, the EMF will remain same, because see, this is minus and this is plus. So, almost these rods are acting just like cells connected in parallel. All negative connected together, all positive connected together. So, the EMF, the net EMF will not be added. It will still be same, whether there is 1 spoke, 2 spokes, 3, 4, 5, whatever. So, this is the net EMF. Similarly, there is another problem of disc being rotated, and if I connect a resistance between again the axle and the rim for this disc, we find that there is an induced EMF here again. And we can find out this value of induced EMF between the center of the disc and the point on the rim. Magnetic field, again let me take it here. So disc is rotating like this, anti-clockwise when looked from the top, and the magnetic field perpendicular to this disc. Here again the way to calculate the EMF is same. I can still take, this is the disc, and I can take, the disc may be supposed to be made up of a large number of rods placed in contact. For one rod, we know what is the EMF. This is, we have just done omega B L square by 2 for one. And we have a very large number, and I just told you that the net EMF will still be same. So in place of R, L, we will have just R, the radius. Same approach we can find out again in the same way. So omega B R square by 2. Sometimes we are given the problems like, okay, I'm giving you a problem of, this is the axle, and again there may be some a very common problem asked in exam, that a train is moving on the rails, and what is the EMF developed at the end of 2 points A and B on the axle. Then just as we have calculated, it is VBL, if V is the speed, L is this length, it will be VL, there will be a potential difference between the 2 points, and this, see, this potential difference, if this is positive or negative, whatever, we may connect it to some source, say a galvanometer, and we can get deflection in the galvanometer. Actually, this technique is used, so when the train is running, there is an EMF developed between the rails, and this is used basically as an indicator that a train is running on this particular track. The requirement is that the magnetic field should have a perpendicular component to this motion. Magnetic field along the motion, no EMF. There is another problem of plane. Again, that is also very common problem, that an aeroplane is flying and you are given the value of the magnetic field, you are also given the value of dip. How to calculate the induced EMF that developed across the two ends of the wings. Then here again, induced EMF is VBL. The only requirement is that many times we are given the magnetic field like this. So with horizontal it is making an angle of theta, so it will be B cos theta component, it will be B sin theta component. So if the plane is moving like this or at some angle, we need the component of field B which is perpendicular to this motion. This will not cause any EMF. So we need B sin theta. Theta is the value of dip at that particular place. Magnetic field should be cut by the rod which is moving in the magnetic field. Only then there will be an induced EMF. So that's all. So we have done the EMF developed across the ends of a rod, conducting rod when it moves in a magnetic field. Then the problem related to wheel or train, plane, motion of disc in a magnetic field, how to calculate the induced EMF between the center and a point on the thread.